Hi Janakiraman.
So last time we were looking at this low pass filter, right? So can we just refresh what we did there?
Absolutely. I believe this is the circuit that you had drawn out last time.
Yes, exactly.
So there is a capacitance, resistance, and an input source. I will call it V in of t.
Yeah, and we had looked at it for a sinusoidal input.
For a sinusoidal input. And
Right.
this one you had called it Vc of t.
Vc of t, right? So
Correct.
I think if we went through the exact differential equation solution and then we got the answer
That's
Vc
right.
of t as
I think your V in of t was some a sin omega naught t,
correct,
right?
and Vc of t
Was, I believe, a by root of 1 plus omega naught squared
r
r
squared
square c squared
into sine
times, oops, sorry, sine of
omega naught t minus phi, I think.
minus
right?
phi, minus
yeah.
phi.
Where tan phi was
Correct, where tan phi
was omega naught rc.
omega naught rc. Perfect.
Right?
That's right.
Omega
I believe
naught.
this is correct.
This is what we got last time,
Correct.
right? And that's why this was a low pass.
I think yes, that's
Filter.
right. We called this like a low pass filter.
Yes, a low pass filter.
That's
Okay.
right. In fact, we did the experiment.
Yes.
We put in sinusoids of same amplitude, kept varying the
Frequency.
and found that the input voltage gets replicated across the capacitor for low frequencies.
Yes.
As you keep increasing the frequencies, it keeps, amplitude keeps reducing.
Diminishing because of this a by root of 1 plus omega naught squared r squared c squared.
That's right. And we saw the phase shift.
Yes.
Right. In fact, on the oscilloscope, we saw the delay kept increasing until it stopped.
Yes.
And then we found that the phase actually goes to 90 degrees.
Saturates at 90 degrees.
Saturates at 90 degrees.
So I think the low pass filter was clear, but I was curious. We looked at the voltage across this capacitor. How does the voltage across the resistor in this circuit look like
Oh, that's very
when I
interesting.
apply a sinusoidal input?
That's very interesting. Okay.
Yeah.
Shall we look at that today then?
Sure, we should do that, or maybe take one step back and say when we apply the step input, first what happens to the voltage across the resistor, and then we'll get to the sinusoid.
Makes a lot of sense. Let's do exactly that.
Okay.
So the only thing I'm going to do is I'm going to call this voltage as VR.
VR, okay?
Okay. So that we have something to represent that variable.
Yes, right.
So now maybe we'll start with something the simplest possible way. Of course, we could do it exactly the same way we did from first principles.
Correct.
But circuit designers, they are always trying to look for different ways of looking at the same circuit.
Exactly. Right.
And sometimes there are better, shorter ways, more elegant ways of solving these things.
Yes, absolutely. And everything should give the same answer.
Everything should give you the same answer. In fact, we have seen several ways of doing this.
Exactly, right?
Right?
We looked at superposition, we looked at differential equation.
Exactly.
I mean, everything should give you the same answer. So
Should
let's
give-
look at another way of
Yes.
doing this.
So maybe what I'm going to do, I'm going to go back to one of the first principles we learned for RC and RLC circuits, which is KVL,
Okay?
right? Kirchhoff's voltage law.
Yeah.
And I am going to apply Kirchhoff's voltage law to this loop because
Yes.
my idea is I see a single loop.
Yeah.
I know that we can apply Kirchhoff's voltage law.
Yes.
So
Correct.
that's what let's start with that.
Okay.
So now from this point to this point,
Yeah.
I have two ways of going there. So I have a way of going here like this and I have a way of going through the loop,
Yeah.
right? So Kirchhoff's voltage laws can be applied in many ways. You can either start from the point, the most basic way is to start from one point, go around the loop and come back to that point.
Same point.
Right? Other people routinely what they say is you go from one point to the other point using two paths, you should get the same potential
answer.
difference.
Correct.
It is exactly the same law, just applied in slightly different ways. Right? So
Okay.
maybe, let's start from basic then. So I'm going to start from this node. So
Okay.
let me call it N1.
Yeah.
I'm going to go around the loop clockwise.
Okay.
Come back to N1.
Come back to N1.
What potential difference has to be 0.
0.
Right? So first I go through the resistor
Yes.
with this reference sign plus and minus sign. So I first get VR of t,
Yeah.
which is a voltage drop,
Yes.
and I get a voltage drop Vc of t.
Yeah.
So I'll use small v maybe for everything.
Yeah.
And then I get a potential increase.
Yeah.
So this is minus
V in of t.
V in of t and this has to be 0.
0.
So
Absolutely.
this is KVL. So KVL literally gives you this
right.
equation. And now I know VR of t in terms of V in of t and VC of t.
Correct.
So, and I also know VC of t in terms of
the input.
The input. So, for this simple circuit,
Okay.
VR of t is simply the difference between the input voltage and the voltage across the capacitor.
Which makes a lot of sense, right? And for step input of V in of t, the VC of t was the exponential charge up, right?
That's absolutely right. So, let's say that we are putting in a step input.
Yeah.
So, my input is a unit step. At t equal to 0, it goes from 0 to 1 volt.
1 volt.
Right? This is V in. So, this is R. The voltage across this is VR. This is C. The voltage across the capacitor
Is
is
VC.
VC.
Excellent. Yeah.
And for this, we found
VC of t.
VC of t was in fact 1 volt times 1 minus e power minus t by RC. I think this was the
Exactly.
equation we derived.
Asymptotic charge. Yes.
That's right. So, what happens is that initially the voltage across the capacitor is 0.
Is 0.
It is completely discharged.
Yeah.
And over time it basically charges to this 1 volt input.
Yeah. 1 volt. Exactly.
Correct. Now, this equation that we wrote here has to be true irrespective of what the input is.
Exactly.
Right? We can actually apply this directly to
the step input.
The step input is right. So, we want to find out VR of t.
VR of t.
So, that has to be equal to V in of t minus VC of t.
Yes.
Right. So, now let us just write this for t greater than 0 because that is what we are interested in.
Yeah.
Right. So, for t greater than 0, V in of t is 1 volt.
V in of t is indeed 1 volt. Yes.
Okay.
Yeah.
And VC of t is this.
This expression.
Because for t less than 0 anyway VC of t is 0.
0. Exactly.
Right, it's just discharged. So, all of this is valid, these two, our expression now is going to be valid for t greater than 0.
Exactly.
Right. So, VR of t is simply going to be 1 volt minus 1 volt into 1 minus e power minus t by RC. So, this is simply nothing but e power minus t by RC in volts.
In volts.
Right.
Okay. Okay, this is interesting. So, and if this were not 1 volt, this would just be V times.
Exactly.
Yeah. Right?
So, you could always say it is not stepping from 0 to 1 volt. It is stepping from 0 to some V naught volts.
V naught volts.
Then, for example, maybe I'll write that in some other color.
Yeah.
If this were some V naught volts,
then
this would be V naught into e power 1 minus e power minus t by RC.
Times, yes.
VR of t would literally be V naught
into this. Exactly.
Into this. Right?
Great.
So, that is what it would look
V
like.
naught times, right.
Correct.
Great. Okay. So, this is sort of seems like a complementary, to this VC of t. Right?
Oh, absolutely. In fact, it should be because you add these two, you should get the input.
You should get back the input, right?
Absolutely.
So, can we just plot this, along with the VC of t on the same graph?
Absolutely. In fact, plotting is very, very important because it helps us, understand so many things.
Yeah, visualizing and seeing those.
Absolutely.
Yeah, seeing is believing in circuits,
right? Absolutely. So, we are plotting both VR and VC.
And VC and also VIN maybe.
VIN. Yeah. So, what I'll do, I'll plot them in 3 different colors.
Exactly.
So, maybe this is my input. So, it goes from 0 to 1 volt.
Yeah.
So, this is 1 volt, this is 0 volts.
Yes.
So, this is VIN of t.
Yeah.
And now VR of t, I'll plot it in this, or VC of
t,
I'll plot
it in let's plot because we already know it.
Correct.
Maybe you can plot in red.
In red?
Looks brighter. Yeah.
Okay. So, now VC of t, so it asymptotically approaches, right? Yeah. So, maybe I'll draw it a little bit better to
show that it asymptotically gets to 1 volt,
something
right?
Like
it never reaches 1 volt.
That's right.
Okay,
so
great.
I'll show it something like this.
Yeah. So, now what happens to VR of t?
So VR of t should actually be the difference between these two.
These two.
Right. So just give me a minute. I'll start labeling this as well. So this is VC of t.
VC of t.
Right. So so 1 minute. So I'll just name these. You are plotting three things on the same graph. So I'm just labeling the axes.
Yes.
Just so that we don't get confused.
Yes.
Right. So VR should simply be the difference between these two.
Yes.
I'm going to say right at the input, the difference is actually 1 volt.
Yeah, because it's 1 minus 0.
Correct. So it actually has to start from here.
Yes.
Okay. See, the V in is constant.
Yes.
So VC is slowly increasing towards it. So this should clearly keep
VR
dropping.
should keep
VR should
decreasing.
Should keep dropping. And I think what will happen is that it will keep dropping to 0 asymptotically. It will never hit 0.
Correct.
You have to wait for infinite time.
Yes.
Before you even hit 0.
Yes.
So I'll just show it as asymptotically hitting 0. Right?
Okay. So interestingly, at what point are these two voltages equal, VR of t and VC of t?
Well,
They seem to be crossing at some point.
They seem to be crossing at some point.
So can we work that out?
Sure. In fact, if the two are equal and if the input is 1 volt, I can take a guess that it should be meeting at half volt. Right?
Exactly, right?
I think I should just be able to look at the circuit and tell that.
Exactly.
Right?
So
if
therefore,
I have two equal voltages and each one should be half a volt.
Half a volt, right? So just go back there.
Yes.
And so this is half a volt on the y-axis.
Yes.
And therefore, the x-axis has to be the number we derived earlier, 0.693 times
Exactly.
the time constant, RC.
That's right.
Right? Okay, great. So what is intuitively, it seems like the capacitor initially is sort of a short circuit and then it's charging up to a final value. The resistor seems to be like a, what, I mean, it's like an open circuit or something at that point. What's happening?
Well, a good way to look at this is if you look at the voltage across the resistor, when the input is 0 and so if you look at time which is just before t equal to 0.
0 minus.
0 minus.
Yes.
So in fact, that would be in this region.
Yeah.
You can also plot all voltages.
Yeah.
And what you will find is that, of course, the capacitor is assumed to be initially discharged. The input voltage is 0. So by definition, the voltage across the resistor also has to be 0.
Yes.
Right? And what is happening? The voltage across the resistor is actually seeing a sudden jump. Exactly like the resistor.
Like the
like the input.
Exactly. Yeah.
Right? And because the capacitor is discharged, you look at it as a short circuit. You will almost get 1 over R. So input voltage 1 by R as the current flowing through the resistor.
Okay. So
at just a time,
just for a small time after 0, right?
That's correct.
So effectively the capacitor has just pulled it to ground. It's like a short circuit to ground, and you have a supply voltage, a DC supply of 1 volt.
That's right.
The resistor going to ground.
So the equivalent circuit at that point, so it will look like this. The capacitor looks like a short circuit. So you have 1 volt and you have R.
And therefore you have a voltage of entire voltage being applied across it, and the current at that point is going to be
1 over R.
1 over R. Okay, interesting, right? Okay, great. And the capacitor, as time progresses, the voltage keeps building. Of course, it can't go beyond 1 volt.
That's right.
And therefore it will saturate at that point.
Correct.
And
at that point, in fact, if you wait for a long enough time, this will be like applying a DC voltage of 1 volt.
Okay.
And we know that for DC voltages, the capacitor is an open circuit.
Okay.
There is no current flowing through the capacitor, and therefore there is no current. So at t equal to infinity, we expect the equivalent circuit to look like this.
Wow. Okay.
Capacitor is an open circuit. So this current is 0.
0, and therefore the voltage
across the resistor is also 0.
Okay. Interesting. So a final quantity that we should probably plot is also this current. You know, we looked at the voltages.
Yes.
But how does the current look in this circuit?
That's very easy to plot because the current through the circuit, there is just one current through the circuit. So, I will mark that current as a current I.
Yes.
That is the current through the resistor. The minute
Yes.
you have plotted the voltage across the resistor, the current through the resistor will just be a scaled version.
Scaled version of
1
that.
over R times VR is the current.
Is the current. Okay, great. Let's look at that then.
So, if this is 1 volt, so let's assume R is greater than 1 ohm.
Yeah.
So, if you were to plot, let me choose this color maybe.
Yeah.
So, this is the current I.
Okay.
I am plotting, and let us say this is 1 over R.
Right.
So, the current jumps and then it will basically follow this 1 over R kind of curve.
So, it starts off with a high current and then it sort of
And then it stops off.
decays.
At any point of time, VR by R would give you the current.
Would give you the current, right? So,
That's
it's
it.
effectively, it's going to be, just go back to the previous page, I guess it's going to follow this expression, e power minus t by RC. 1 by R
Absolutely.
times e power minus I of t will be 1 over R
Correct.
e
1 over
power
R,
minus
e power minus T by
RC.
RC. Amperes.
Amperes, right? In amperes. Okay, excellent. So, right. So, this has given us a feel, you know, for what the resistor does to the step response. Now, can we take this forward to sinusoids as well? What happens when I apply the sinusoid, right?
Absolutely. So, let us say we apply a sinusoidal input to the circuit. So, your input is a sinusoid,
Yes.
and last time we saw, I think we also mentioned it at the beginning of the class, you will get a phase shifted voltage across the capacitor
Yes.
and so on.
Yes.
Now, we can use this KVL just like we did to calculate this voltage and current as well in this case. So, in fact, we will do that. So, VR of t
Is
has
equal
to be equal to V in of t minus Vc of t.
Of t.
So, this is Vc of t, this is VR of t, and this
Okay.
is Vn of t.
Right.
And last class, Vn of t is, we said A sin omega
A sin
t
omega naught t. Okay.
minus Vc of t was simply A by root of 1 plus omega naught squared R squared C squared time,
minus phi.
sorry, minus
minus
5, correct, that's right.
Right, where again tan phi was omega naught RC.
That's right.
Okay, so this is what the voltage across the resistor looks like. Now, intuitively, can you just, you know, tell me what happens for low frequencies, high frequencies?
Yes. So, what we will do, just like we did last time, we will start from a very low frequency. Last time I think we started from 100 hertz.
Yeah.
Then we went in steps.
Yes.
Some non-linear steps, but then we went from maybe 100 hertz to 100 kilohertz
Correct.
and found out what happens.
Yeah.
Right. In this case, we can look at this analytical form
Yeah.
and tell what is going to happen. So, most likely, if you start from a very low omega naught,
Yeah, again low is with respect to the 1 by RC.
with respect to 1 by RC.
1 by RC.
Right.
Yeah.
So, if you start off with omega naught much smaller than, so
1 over RC.
1 over
Right.
RC,
Yeah.
right. If you do this,
Yes.
so then what happens is omega naught RC is much smaller than 1.
Yes.
So, this portion will become
A
very
is
close to A. The denominator will become very close to 1,
Yes.
and the phase shift is very small.
Tan phi is omega naught RC.
Correct.
Right.
Correct.
This
So,
was tan.
it
is
was very close to
approximately
it's 0, very small.
Yeah.
What happens is that the input voltage is going to be the, or rather the capacitor voltage is going to follow the input voltage
for low frequencies.
for low frequencies,
Right.
which means the resistor voltage is going to be very small.
Small. Exactly.
Okay. So, in this case, VR is small. So, in fact, amplitude,
Yeah.
right?
Okay.
is going to be small.
Interesting. Okay.
Right? Now we can look at the other extreme.
Yes.
So we can look at the other extreme is much greater than 1 by RC.
That means omega naught RC is much greater than 1.
Yes. So in fact, I'll write it in maybe a different color.
Yeah.
So, okay.
Yeah.
If you do this, now this term here
Yes.
is actually going to become very close to A by
Omega
naught RC.
RC. Correct.
Okay. And if you choose a very large omega naught, this amplitude is going to be very small.
Very small. Exactly.
So which means you are subtracting out some very small quantity from A sin omega t.
Yes.
You will just be left with most likely A sin omega t.
T itself. Okay.
Right. So in fact, your VR will be, this is what you will get. You will get A. You will get the original amplitude.
Amplitude.
Right.
Okay. And just to clarify, what happens to the phase? Tan phi is omega naught RC, and we are saying that goes to a very large value.
That's right.
So it should go to pi by 2.
It should go to pi by 2.
It should go to pi by 2. But the amplitude is so small.
Amplitude is so small.
So I don't care if this is sine or cos.
Exactly.
Right?
You don't care about the, because if this overall sinusoid becomes very small, once you subtract it from a much larger amplitude sinusoid, you will notice very little difference.
Very little difference. So the phase doesn't matter in this argument. So you seem to be suggesting that the resistor voltage is doing exactly the opposite of the capacitor voltage.
That's right. In our original circuit, I think what we found is when omega naught RC was much less than 1, right, when omega naught was small, you actually got, in this case, the capacitor voltage actually followed the input voltage. Right? But now the resistor voltage is the capacitor voltage subtracted from the original one. So you are seeing the exact opposite behavior.
Exact opposite behavior. So
yes.
What does this actually suggest? It seems to suggest that it is like letting some high frequencies through.
Yes.
But it is cutting out low frequencies.
So because we call the other one low pass filter, we should probably call this a high pass filter.
Yes, makes sense.
Right. So we call this
is a high pass filter.
We'll call this a high pass filter.
Okay, interesting. Okay, so this is this is very nice. So, but the only things that sort of troubling me is I'm measuring a voltage across a resistor. I'm more comfortable measuring it across ground somewhere.
Across ground.
Can you redraw this so that?
Let's do that.
It looks more comfortable that way?
Yes. So we will redraw the same circuit. So let's start with this. Let us see if we can redraw it to something easier.
Okay.
Right. So this is R, and so originally we had this as reference.
Yes.
So right now I'm not going to draw the reference immediately, but for measurement, as you pointed out, it is a lot easier.
Yeah.
Right. So now if this is, so let's call this N1 as before, and we'll call this N2, and we'll call this N3. We have 3 nodes in this circuit.
Yeah.
Right. So, and this is VR.
Correct.
Now, suppose we flip the signs of the input.
Okay.
Okay. We know from superposition that the voltages and current should also flip signs.
Flip signs. Yes.
Right. So let us. The first transformation we are going to do is this. So we will redraw it like this.
Yeah.
So this is still N1, N3 and N2.
Yeah.
Except now if you apply V in like this.
Yeah.
In this direction you will actually get minus Vc.
Minus Vc, correct.
Right, because you have changed wherever you had Vc as a function of V in, you will get minus V in.
Okay, right.
Okay. So this VR, you will get it as minus VR.
Right.
Right. And your KVL, KCL will still be valid.
Yes.
So this is purely from superposition.
Yes, superposition theorem, yeah. Right.
Okay. So now let us just redraw it such that the positive is on the top.
Okay.
That's easier, no? We are comfortable with the negative being on the top and positive being on the, positive being on top and negative being on the bottom. So let's redraw it like that. So all I'm going to do, I'm going to take this particular circuit here and just flip it along a horizontal axis.
Okay. So you're going to just mirror it about the x-axis.
About the x-axis.
Okay. Okay. Great.
So I'm going to draw it like this, and let us see. I have plus Vin on top.
Yeah.
The plus terminal.
Yes.
So this now becomes N3 and this becomes N1.
N1. Correct.
And now between N1 and N2 I have a resistor.
Yeah.
So I am moving this here.
Yes.
It gets flipped to the bottom. So, and then I have a capacitor here between N2 and N3.
Okay.
Okay. So I had capacitance between N2 and N3 here.
Yeah.
And I have the same thing here as well between N2 and N3.
Between N2 and N3. Yes.
Right.
Right.
And now all I have to do is rearrange it such that now my negative terminal is what I wanted to have as a reference.
Correct.
So all I have to do is I'm just going to redraw the circuit. It's just a different way. I'm going to draw the capacitor in series like this.
Yes.
And the resistor in shunt like this.
Oh, so you have just taken
elongated one, exactly. I've just moved C to the upper side.
You have rotated that anti-clockwise.
That's all I've done.
Right? That's all.
So this is still V in.
Yeah.
Node N3 is here.
Yes.
Node N2 is here. Node N1 is here.
Wow.
Okay. Now all I have to do is make this node my reference ground.
Ground. Okay. And then you are measuring the voltage across the resistor. VR.
This would be VR. This would be VC.
Wonderful.
Okay. You will still have Vin being equal to the sum of VR and VC.
VC, yeah.
If you applied an input step, VC would, be Vin step, the final value into 1 minus e power minus t by RC.
RC, right.
This VR would be the final value times e power minus t by RC and so on.
Yes.
Because the circuit is exactly the same, we have just done two things. We have applied superposition theorem, applied the negative of the voltage, redrawn the circuit.
Redrawn the circuit a little bit. Okay.
Yes.
So this is wonderful. So therefore, if we now look at a circuit, on the breadboard like this, and then do the exact same experiment that we did last time, that is keep the amplitude fixed and just sweep the frequency, we should see the behavior of a high pass filter.
That's absolutely right. So let us do that now.
Yeah.
Right. So this is my high pass filter. In fact, a lot of textbooks prefer to draw it like this.
Yes.
Because it's easy to measure and the output is coming from the right side, input is being applied on the left side, which is the natural convention.
Yes.
So let's go on to the experiment then.
Yeah, let's go on. I think let's just note down the values. It's a 100 nanofarad capacitor.
So
okay, and the resistor seems to be 1.2 kilo ohms.
1.2 kilo ohms. Oh, this is very similar to the numbers we used last time for the low pass filter.
Exactly. So what did we get? We got about 10 milliseconds or something? 10
milliseconds, that's right. So the RC time constant is basically, rather it is about 120 microseconds.
Let's say 100 microseconds.
Let's say 100. Let's make things easier for us. So maybe we'll just write it as 1 kilo.
Yeah.
Right? So 1 kilo ohm times 100 nanofarad is 100 micro.
Yes.
Seconds,
right? And this was like 10 kilohertz.
This was 10 kilohertz.
This was approximately some number like that,
correct,
right?
Something like 10 kilohertz.
Okay, great.
Or rather 10 kilo radians per second.
Radians per second, yeah.
Correct.
Let's not forget that.
Yes.
Okay.
So it was 10 kilo radians per second. The frequency in hertz was this divided by 6.28 by 2 pi.
By 2 pi, yes.
Right.
Okay.